So here's something that might surprise you. The idea behind string theory, this thing that people call the most ambitious, most abstract, most mathematically intimidating framework in all of physics, it didn't start with someone trying to explain the universe. It started with someone trying to explain the inside of a proton. And the year was 1968, and the person was a young Italian physicist named Gabriele Veneziano, and he was sitting at his desk at CERN, the big particle physics lab near Geneva, flipping through a dusty mathematics textbook when he stumbled across a formula that had been written down almost 200 years earlier by a Swiss mathematician named Leonhard Euler. And Veneziano looked at this formula, this thing called the Euler beta function, and he realized, almost by accident, that it perfectly described certain patterns he'd been seeing in experiments where protons were smashed together at high energies. But we're getting ahead of ourselves. Let's slow way down. Because if you're lying there tonight wondering what string theory actually is, and why physicists have spent 50+ years arguing about it, and whether any of it matters to you personally, well, I want to walk you through the whole story, gently, from the very beginning. And I mean the real beginning, not the beginning that textbooks give you, but the messy, human, confused, beautiful beginning where nobody knew what they were building. So let's start with something you already understand, even if you don't think you do. You know what a particle is, right? At least intuitively. An electron, a proton, a photon of light. These are the tiny building blocks that make up everything. You, the bed you're lying on, the air in the room, the phone or speaker playing this right now. For most of the 20th century, physics made extraordinary progress by treating these things as points, tiny, dimensionless dots. A particle, in the standard picture, has no width, no length, no height. It's just a point that sits at some location in space, has some mass, has some charge, and obeys certain rules. And that picture works astonishingly well. I mean, quantum mechanics and quantum field theory, the mathematical frameworks built on this idea of point particles, they've given us the most precisely tested predictions in the history of science. The magnetic moment of the electron, for instance, has been calculated to something like 10 decimal places and matches experiment perfectly. 10 decimal places. That's like predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. So when someone tells you that point particles are a useful idea, they're not kidding. But here's the thing. There's a problem, and it's a deep one. And physicists have known about it for a long time. The problem is gravity. See, we have two incredibly successful theories in physics. On one side, you've got quantum mechanics and its more sophisticated cousin, quantum field theory. These describe three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. They describe how particles interact, how light works, how atoms hold together, how radioactive decay happens. And they do all of this with breathtaking precision. On the other side, you've got general relativity, Einstein's masterpiece, published in 1915. This describes the fourth force, gravity, and it does so by reimagining what gravity even is. In Einstein's picture, gravity isn't really a force at all. It's the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space and time around them, and other objects follow those curves. That's why the Earth orbits the Sun. It's not being pulled by some invisible rope. It's rolling along the curved geometry that the Sun creates in space-time. And general relativity has been tested over and over. GPS satellites have to account for it. Gravitational waves have been detected exactly as Einstein predicted. Black holes behave the way the equations say they should. So you've got two theories, both spectacular, both confirmed by mountains of evidence, and they absolutely refuse to work together. Think about what that means. If you want to describe something very small, an electron, a quark, you use quantum mechanics. If you want to describe something very massive, a star, a galaxy, the expansion of the universe, you use general relativity. But what happens when you need both? What happens when something is both incredibly small and incredibly massive at the same time? And that's not a hypothetical. There are places in the universe where exactly this situation arises. The center of a black hole, for instance. All the mass of a collapsed star crushed down into a point of essentially zero size, or the very first instant of the Big Bang, when the entire observable universe was compressed into a region smaller than an atom. In those situations, you need a theory that combines quantum mechanics and gravity. You need quantum gravity. And when physicists try to combine them using the standard tools, when they try to apply quantum field theory to gravity, treating the graviton, the hypothetical particle of gravity, as just another point particle, the math breaks. Not in a subtle way. It breaks catastrophically. You start getting infinities everywhere. Calculations that should give you sensible answers instead give you infinity. And not the kind of infinities that you can tidy up with clever tricks, which is something physicists actually do all the time in other contexts. There's a whole technique called renormalization that lets you sweep certain infinities under the rug in a controlled, mathematically rigorous way. But with gravity, the infinities can't be tamed. They multiply. Every time you try to fix one, two more pop up. The theory is, in the technical jargon, non-renormalizable, which is a fancy way of saying it doesn't work. The math is telling you that something about your assumptions is fundamentally wrong. And this has been the central, unsolved problem in theoretical physics for the better part of a century. How do you reconcile quantum mechanics with general relativity? How do you build a theory of quantum gravity? Now, there have been several approaches to this problem over the decades. Loop quantum gravity is one. Causal set theory is another. But the one that has attracted the most attention, the most talent, the most passion, and also the most controversy, is string theory. And the basic idea, the seed of it, the thing that makes it different from everything else, is breathtakingly simple to state, even if the details get wonderfully complicated. What if particles aren't points? What if, instead of being zero-dimensional dots, the fundamental objects in the universe are tiny, one-dimensional loops or strands of something? Let's call them strings. Not literal strings like on a guitar, but something more abstract. Little filaments of energy, unimaginably small, vibrating in different patterns. And here's the key insight. Different vibration patterns correspond to different particles. One pattern of vibration looks like an electron. Another looks like a quark. Another looks like a photon. And this is the part that made people's jaws drop. One particular vibration pattern automatically, unavoidably, looks like a graviton, the particle that carries the force of gravity. In other words, gravity isn't something you have to shoehorn into string theory. It shows up on its own, uninvited, inevitable. And when you work out the math, the infinities that plagued the point-particle approach to quantum gravity, they go away. The extended nature of the string, the fact that it has a tiny but non-zero length, smears out the interactions in a way that tames those infinities. It's as if the string's own size acts as a natural regulator, softening the violent, point-like collisions that made the old calculations blow up. And that, right there, is why string theory has captivated so many brilliant people for so many decades. It's the only known framework that naturally, organically, without any forcing, combines quantum mechanics and gravity into a single, consistent picture. But let me take you back to where this all started, because the origin story is wonderfully strange. Nobody set out to build a theory of everything. Nobody was trying to unify gravity with quantum mechanics. The whole thing began in the late 1960s in the world of particle physics with a very specific and much more modest puzzle. In the 1960s, physicists were smashing protons and other particles together at higher and higher energies, and they kept discovering new particles. Lots of them. An embarrassingly large number of them. They called them hadrons, particles that interact via the strong nuclear force. And there were so many of them that the whole situation was sometimes called the particle zoo. There were pions and kaons and rho mesons and omega baryons and dozens more, and nobody had a clean, simple theory that explained why there were so many or how they were related. Some physicists, rather than trying to build a detailed theory of what was going on inside these particles, took a different approach. They said, look, let's just try to find mathematical patterns in the data. Let's look at how these particles scatter off each other and see if we can find formulas that describe the results, even if we don't fully understand why those formulas work. This approach was called S-matrix theory, and it was championed by a brilliant and somewhat contrarian physicist at Berkeley named Geoffrey Chew. Chew's philosophy was radical for the time. He argued that you didn't need to know what the fundamental constituents of matter were. You just needed to know the rules governing how particles interacted, the inputs and outputs of collisions. The S-matrix, or scattering matrix, was the mathematical object that encoded all of that information, and it was within this intellectual atmosphere that Gabriele Veneziano made his discovery. Veneziano was trying to find a mathematical formula that would describe how certain mesons, specifically pions, scattered off each other. He wanted a formula with very particular properties that the S-matrix theorists had argued any good theory of the strong force should have. And one day, he recognized that the Euler beta function, this piece of pure mathematics from the 18th century, fit the bill almost perfectly. He published his result in 1968, and it was a sensation within the small community of people working on this problem. But here's the thing. Veneziano's formula worked, but nobody understood why it worked. It was a formula without a physical picture. It described the data, but it didn't tell you what was actually happening when those particles collided. It was like having a recipe that produces a delicious cake, but having no idea what an oven is or why flour and eggs behave the way they do. And then, in 1970, 3 physicists, working independently in different parts of the world, figured out what Veneziano's formula was secretly describing. Yoichiro Nambu in Chicago, Holger Beck Nielsen in Copenhagen, and Leonard Susskind in New York. Each of them, through different paths of reasoning, arrived at the same stunning conclusion. The formula made sense if you imagined that the particles weren't points. If you imagined that, deep down, they were tiny vibrating strings. Susskind's story is particularly wonderful. He was a young professor, relatively unknown at the time, and he later recalled staring at Veneziano's formula and trying to visualize what kind of physical system could produce it. And he realized that the mathematical structure of the formula was identical to what you'd get from a relativistic string, a one-dimensional object, stretching and vibrating, with its endpoints moving at or near the speed of light. The different energy levels of the string's vibrations corresponded to different particles. The whole zoo of hadrons, all those mesons and baryons, might just be different notes played on the same tiny string. It was an electrifying idea, and it was also, as it turned out, wrong. Or at least, wrong for its original purpose, because within just a few years, a completely different theory came along to explain the strong force, quantum chromodynamics, or QCD, which described protons and neutrons as being made of quarks held together by gluons. QCD worked beautifully, and it didn't need strings at all. The string model of hadrons was effectively abandoned by mainstream particle physics by the mid-1970s. And you might think that would be the end of the story, a clever idea that didn't pan out. But something remarkable happened. A few stubborn, brilliant people kept working on string theory, even after it fell out of fashion. And they started noticing things. Strange, beautiful, unexpected things. The theory kept producing results that seemed too elegant to be meaningless. And one of those results, perhaps the most important one of all, was discovered by a young French physicist named Joel Shirk and an American physicist named John Schwartz, working together at Caltech in the early 1970s. They noticed that among the vibration modes of the string, there was one that had zero mass and spin 2. And if you know a little bit about particle physics, that combination, massless, spin 2, is incredibly specific. There's only one known particle that fits that description, and it's the graviton, the hypothetical quantum carrier of gravity. Shirk and Schwartz looked at this result, and they made a leap that was either audacious or crazy, depending on who you asked. They said, what if string theory isn't a theory of the strong force at all? What if it's a theory of everything, including gravity? What if the reason this graviton keeps showing up in the math is because string theory is secretly a theory of quantum gravity, and we've just been thinking about it at the wrong scale? Because here's a crucial detail. In the original hadronic string theory, the strings were imagined to be about the size of a proton, roughly 10 to the minus 15 meters. But if you reinterpreted the theory as a theory of gravity, the strings would need to be much, much smaller. Down at something called the Planck length, about 10 to the minus 35 meters. That's so small that if you blew an atom up to the size of the observable universe, the Planck length would still be smaller than a single grain of sand in your hand. That's the kind of smallness we're talking about. It's not just small compared to everyday things. It's small compared to the smallest things physicists had ever measured. The Planck length sits at the very basement of physical reality, the scale where the smooth fabric of space-time itself is supposed to break down into something foamy and quantum and strange. And Shirk and Schwartz were saying that this is where strings live. Not up at the nuclear scale, where people had been looking, but way, way down there, at the absolute foundation of everything. Now, you'd think a claim like that, hey, we might have stumbled onto a theory of quantum gravity, would have set the physics world on fire. But it didn't. Not even close. And there are a few reasons for that, and they're worth understanding, because they tell you a lot about how science actually works, which is messier and more human than people usually admit. First, the timing was terrible. This was the mid-1970s, and quantum chromodynamics, QCD, was having its moment. The theory of quarks and gluons was explaining the strong force beautifully, and it was doing it with point particles, the way everyone was comfortable with. Experimentalists were confirming predictions left and right. The standard model was coming together like a puzzle where the pieces were finally clicking into place. So here come Shirk and Schwartz saying, actually, forget about strings for the strong force. But don't throw the theory away because it might be a theory of gravity instead. And most physicists just kind of shrugged. Gravity? Quantum gravity wasn't really a pressing experimental problem. There were no experiments anywhere near the Planck scale. There still aren't, honestly. So the whole idea felt academic in the worst sense. Interesting maybe, but untestable, and therefore not worth spending your career on. Second, string theory at this point had some genuinely weird features that made people uncomfortable. And this is where we need to talk about one of the strangest things about the theory, something that had been lurking in the math from the very beginning, and that Shirk and Schwartz didn't solve, they just reframed. The thing is this: string theory only works mathematically in a specific number of dimensions. Not 4, which is what we experience. 3 of space, plus 1 of time. Not 5, not 7. The original bosonic string theory, the one that grew out of Veneziano's formula, required 26 dimensions to be mathematically consistent. 26. And if you tried to formulate it in fewer dimensions, the math broke. Anomalies crept in. Symmetries that were supposed to hold didn't hold, and the whole structure fell apart. Now 26 dimensions sounds absurd, and it is kind of absurd, but let me explain what mathematically consistent means here, because it matters. When physicists build a quantum theory, there are certain rules it has to obey. Conservation of probability is a big one. The total probability of all possible outcomes has to add up to 1, always. If your theory violates that, it's not just wrong, it's nonsensical. It's like a weather forecast that says there's a 130% chance of rain. In string theory, when you quantize the vibrating string, when you apply the rules of quantum mechanics to it, you find that these consistency conditions pin down the number of dimensions. The math is telling you something. It's saying, I only work if the universe has this many dimensions, and you can either listen to the math or walk away from the theory. Here's the thing, though. By the time Shirk and Schwartz were working on their gravity proposal, a newer version of string theory had appeared that brought that number down. This is where supersymmetry enters the picture. And it's one of those ideas that sounds like it was invented to solve one problem, but turns out to solve about 5 problems at once. Supersymmetry, people usually just call it SUSY, is a proposed symmetry between the two fundamental categories of particles in nature, bosons and fermions. And let me unpack that for a second because it's actually pretty intuitive once you see it. Every particle in the universe falls into one of 2 camps. Bosons are the force carriers, photons, gluons, the W and Z bosons, and the hypothetical graviton. They're the particles that transmit interactions. Fermions are the matter particles, electrons, quarks, neutrinos, the stuff that makes up you and me and everything solid. The distinction comes down to a quantum property called spin. Bosons have integer spin, 0, 1, 2. Fermions have half-integer spin, 1/2, 3/2. And this seemingly small difference leads to radically different behavior. Fermions obey the Pauli exclusion principle, which is why electrons in an atom stack up in shells instead of all collapsing to the lowest energy state. That's literally why chemistry works, why the periodic table has structure, why matter is solid. Bosons don't obey that rule. They can pile up on top of each other, which is how you get lasers, where trillions of photons occupy the exact same quantum state. So these 2 families of particles seem fundamentally different. But supersymmetry says, what if there's a deep symmetry connecting them? What if every boson has a fermion partner, and every fermion has a boson partner? The electron would have a bosonic partner called the selectron. The quark would have the squark. The photon would have the photino. The graviton would have the gravitino. These partner particles, the superpartners, haven't been observed, which is a significant issue we'll come back to. But the mathematical structure of supersymmetry is extraordinarily beautiful and powerful. When you incorporate supersymmetry into string theory, several things happen. The most dramatic is that the required number of space-time dimensions drops from 26 to 10. That's still 6 more than we observe, but it's a lot better than 22 extra. And the theory also becomes much better behaved. Remember, the original bosonic string theory had that tachyon problem. A particle that moves faster than light, which signals an instability in the theory, like a ball sitting on top of a hill instead of in a valley. Supersymmetry gets rid of the tachyon. It stabilizes the theory. It also naturally includes fermions in the spectrum of string vibrations, which the original bosonic theory didn't. It only produced bosons, which is obviously a problem if you want to describe a universe that contains matter. This supersymmetric version became known as superstring theory, and it was developed through the 1970s by several people, including Pierre Ramon, André Neveu, and John Schwarz himself. Ramond figured out how to add fermions to the string in 1971, and Neveu and Schwarz worked out a consistent bosonic sector to go with it. The full picture took years to assemble, and it wasn't always clear that it would hang together. But by the late 1970s, superstring theory existed as a mathematically coherent framework, a theory of tiny strings vibrating in 10 dimensions, producing both bosons and fermions, including a graviton, with no tachyon and no anomalies. And almost nobody cared. This is the period people sometimes call the string theory wilderness years, roughly 1975 to 1984. Schwarz kept working on it, almost alone among established physicists. He later said that he felt like he was working on the most important problem in physics and couldn't understand why no one else was interested. Michael Green, a British physicist, joined him as a collaborator, and the two of them spent years working through the technical details of superstring theory together, mostly at Caltech and at various European institutions. They were a small team working on an unfashionable problem, and that takes a particular kind of stubbornness, or faith. Maybe both. But here's what's worth appreciating about that period. Even though the physics community had largely moved on, the theory kept revealing internal structure that was hard to dismiss. Every time Green and Schwarz pushed deeper into the mathematics, they found more consistency, more elegance, more unexpected connections. It was as if the theory wanted to work. And I know that's a strange thing to say about a set of equations, but mathematicians and physicists both talk about this feeling, the sense that you're not inventing something, but discovering it, that the structure was already there waiting for someone to notice. And then, in 1984, something happened that changed everything. Green and Schwarz published a paper that solved a problem many people thought was fatal to string theory. The problem was about anomalies, specifically quantum anomalies that would break the gauge symmetries the theory needed to describe the real forces of nature. An anomaly, in this context, is when a symmetry that exists in the classical version of a theory gets destroyed when you quantize it. It's a quantum effect that spoils the math, and there was a widespread belief that superstring theory in 10 dimensions would inevitably have these anomalies, which would make it inconsistent. Basically dead on arrival as a serious theory. Green and Schwarz showed that this wasn't true. They demonstrated that for a very specific choice of gauge group, a mathematical structure called SO32. All the anomalies canceled, every single one. The cancellation was intricate and precise, involving a delicate interplay between different types of anomalies that had to balance exactly. And the fact that they did balance, for this particular gauge group and not for random ones, felt like the theory was selecting its own ingredients. It wasn't that you could plug in any symmetry group and get a consistent theory. The math was telling you which groups were allowed, and it was extremely picky. This result hit the physics community like a thunderclap. It became known as the first superstring revolution, and almost overnight, string theory went from a backwater pursued by a handful of diehards to the hottest topic in theoretical physics. Within months, hundreds of physicists pivoted their research programs to work on strings. Edward Witten, who was already one of the most respected theorists in the world, called string theory the most important development in physics in decades. And when Witten says something like that, people listen. He has an almost legendary ability to see deep mathematical structure, and his endorsement carried enormous weight. But the Green-Schwarz anomaly cancellation wasn't just a technical result. It opened a door to something bigger. Because very shortly after their paper, a group of 4 physicists, David Gross, Jeffrey Harvey, Emil Martinek, and Ryan Rohm, all at Princeton, discovered a new type of string theory that used a different gauge group, E 8 times E8. This group, E8, is one of the most extraordinary mathematical objects ever discovered. It's a Lie group with 248 dimensions, and its structure is so rich and intricate that mathematicians had been studying it for a century before it showed up in physics. And here it was, emerging naturally from the requirement that a 10-dimensional string theory be anomaly-free. The theory Gross, Harvey, Martinek, and Rohm constructed became known as the heterotic string, and it was a genuinely strange and beautiful creation. Here's what's clever about it. A closed string, a little loop, has vibrations that travel in 2 directions around the loop, clockwise and counterclockwise. The heterotic string treats these 2 directions differently. The clockwise moving vibrations are described by a superstring theory in 10 dimensions. The counterclockwise moving vibrations are described by the old bosonic string theory in 26 dimensions. And you might think, wait, how can the same string live in 10 dimensions going one way and 26 going the other? The answer is that 16 of those 26 dimensions are compactified, curled up, in a very specific way that encodes the E8 times E8 gauge symmetry. It's like the string is carrying extra information in its left moving vibrations, information that manifests as the symmetry groups needed to describe the forces of nature. And here's why that mattered so much. The E8 times E8 gauge group is large enough to contain the symmetry groups of the standard model, the SU 3 times SU 2 times U1 that describes the strong, weak, and electromagnetic forces. So for the first time, people could imagine a single theory, a theory of strings vibrating in 10 dimensions that naturally incorporated both gravity and the other 3 forces. Not because someone had bolted them together by hand, but because the mathematical consistency of the theory demanded it. The excitement in 1984 and 1985 was palpable. People were talking about a theory of everything, and they meant it seriously. But there was still that nagging issue, the one I mentioned a few minutes ago and then set aside. 10 dimensions. The theory needs 10 space-time dimensions to work, and we only see 4. So where are the other 6? This is where an idea from the 1920s gets a spectacular second life, and it involves a Polish mathematician named Theodor Kaluza and a Swedish physicist named Oskar Klein, And what they proposed is one of those ideas that sounds completely insane until you think about it for a while. And then it starts to seem not just plausible, but almost beautiful. So here's what Kaluza did. Back in 1919, he was sitting with Einstein's equations of general relativity, the ones that describe gravity as the curvature of space-time in 4 dimensions, 3 of space and 1 of time. And he asked a question that nobody had any particular reason to ask. What if space-time has 5 dimensions instead of 4? What if there's one extra spatial dimension that we just haven't noticed? And when he worked through the math, when he wrote down Einstein's equations in 5 dimensions instead of 4, something remarkable fell out. The equations naturally split into 2 parts. One part was ordinary 4-dimensional gravity, exactly as Einstein had described it. And the other part, and this is the part that made Kaluza's heart race, was Maxwell's equations. Electromagnetism, the complete theory of electric and magnetic fields, just sitting there inside 5-dimensional gravity, as if it had been waiting to be found. Think about what that means. Kaluza didn't add electromagnetism by hand. He didn't stitch 2 theories together. He simply wrote down gravity in 1 extra dimension, and electromagnetism emerged on its own. 2 forces that seemed completely different in 4 dimensions turned out to be the same force viewed in 5 dimensions. It's like discovering that 2 strangers you've known your whole life are actually siblings. The family resemblance was always there. You just needed the right angle to see it. Now, the obvious question: if there's a 5th dimension, why can't we see it? Why don't we move through it the way we move through the other 3 spatial dimensions? This is where Oscar Klein came in, around 1926. Klein proposed that the extra dimension is curled up, compactified, into an incredibly tiny circle. Imagine a garden hose. From far away, a garden hose looks like a 1-dimensional line. You see its length, and that's it. But if you were an ant walking on that hose, you'd know there's another dimension. You could walk around the circumference. The hose has length, and it has a circular cross-section, but the circular part is so small compared to the length that from a distance, you miss it entirely. Klein said the 5th dimension is like the circumference of that hose, but unimaginably smaller, curled up at roughly the Planck length, about 10 to the minus 35 meters. That's 100 billion times smaller than a proton. No experiment we could ever build would directly resolve something that tiny. So the dimension is there. It's real. It's part of the geometry of space-time, but it's hidden from us because it's compactified at a scale far below anything we can probe. And here's what's really clever. The way a field wraps around that tiny circular dimension, the number of times it winds around, the momentum it carries in that direction, those things look, from our 4-dimensional perspective, like electric charge. The quantization of electric charge, the fact that charge comes in discrete units, falls out naturally from the fact that the extra dimension is a circle. If you go around a circle, you have to come back to where you started, and that periodicity forces the momentum in that direction to be quantized. Charge isn't some mysterious property bolted onto particles. It's momentum in a hidden dimension. That's a gorgeous idea. So Kaluza-Klein theory sat there for decades, a beautiful curiosity that never quite led anywhere, because, well, one extra dimension gives you electromagnetism, but the universe has more forces than that. You need the strong force and the weak force too. And to get those, you'd need more extra dimensions with more complicated shapes. In the 1920s and 1930s, nobody knew how to make that work. And honestly, nobody had strong enough reasons to try. Quantum mechanics was exploding with discoveries. Nuclear physics was opening up. and the Kaluza-Klein idea drifted to the margins. But now fast forward to 1985. String theory needs 10 dimensions. You live in 4. That means 6 dimensions need to be compactified, curled up, hidden. And the shape of those 6 curled up dimensions isn't arbitrary. It matters enormously. The shape determines everything. It determines which particles exist, what masses they have, how many generations of quarks and leptons there are, what the coupling constants of the forces are. The geometry of those hidden dimensions is, in a very real sense, the source code of our universe's particular physics. So what shape should those 6 extra dimensions take? This is where a class of mathematical objects called Calabi-Yau manifolds enters the story, and the way they entered is itself a nice tale about mathematics and physics feeding each other. In 1957, a mathematician named Eugenio Calabi, working at the University of Minnesota, proposed a conjecture about a certain class of complex geometric spaces. These were compact Kähler manifolds. Don't worry too much about the technical name. Just think of them as higher dimensional shapes that satisfy some very specific geometric conditions. Calabi conjectured that if such a space satisfies a certain topological condition, specifically if its first Chern class vanishes, then it must admit a special kind of metric, a way of measuring distances on it, called a Ricci-flat metric. Ricci-flat means, roughly, that the space has no intrinsic curvature of a particular kind. In the language of general relativity, a Ricci-flat space is one that satisfies Einstein's vacuum equations. No matter, no energy, just pure, empty space-time geometry. So Calabi was asking, if a shape has the right topological properties, does it necessarily have this very special, very elegant geometry? For nearly 20 years, nobody could prove it. Some mathematicians suspected it was false. Then, in 1976, Xingtung Yao, a young mathematician who had recently moved to Stanford, proved that Calabi was right. The proof was a tour de force, and it earned Yao the Fields Medal in 1982. These spaces became known as Calabi-Yau manifolds, and at the time, they were objects of pure mathematical interest. Nobody was thinking about physics. Nobody was thinking about hidden dimensions. They were just beautiful geometric structures that happened to satisfy a deep and surprising theorem. And then string theory came knocking. In 1985, Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten published a landmark paper showing that if you compactify the 6 extra dimensions of string theory on a Calabi-Yau manifold, you get exactly the kind of 4-dimensional physics that could resemble our world. The Ricci flatness condition is precisely what's needed for the compactification to preserve supersymmetry, to keep the nice mathematical properties of the 10-dimensional theory intact as you reduce to 4 dimensions. And the topology of the Calabi-Yau, its shape, its holes, its twists, determines the particle content of the 4-dimensional theory. Here's an analogy that might help. Imagine you have a trumpet. The sound a trumpet makes depends on its shape, the length of the tubing, the flare of the bell, the diameter of the bore. Different shapes produce different overtone series, different timbres. Now imagine the Calabi-Yau manifold as the shape of a 6-dimensional trumpet, and the vibrations of the strings as the notes it can play. The geometry of the manifold determines which vibrational modes are possible, and those modes are what we perceive as different particles with different properties. Change the shape of the Calabi-Yau, and you change the physics of the universe. And this is where things got both incredibly exciting and deeply troubling. Exciting, because people could actually start computing things. You pick a specific Calabi-Yau manifold. You work out its topology, specifically things called Hodge numbers, which count the different types of holes in the manifold. And those numbers tell you how many generations of particles your four-dimensional theory has. One particular class of Calabi-Yau manifolds has Hodge numbers that give you exactly 3 generations of quarks and leptons, which is what we observe in the real world. 3 generations: the up and down quarks, the charm and strange quarks, the top and bottom quarks, with their corresponding leptons. The fact that a specific geometric choice could reproduce that number felt like a sign that the theory was on the right track. But here's the troubling part. There isn't one Calabi-Yau manifold. There are many. By the late 1980s, mathematicians had constructed thousands of them, and it became clear that the number was vast. Each one gives you a different four-dimensional physics, different particle spectra, different coupling constants, different cosmological constants. And the theory itself doesn't tell you which one to pick. There's no equation in string theory that says, this Calabi-Yau is the right one and all the others are wrong. They're all equally valid solutions. This is the landscape problem, and it would grow into one of the most contentious issues in all of theoretical physics. But that's a story for a bit later. For now, let's stay in the late 1980s and appreciate the mood. Because despite the embarrassment of riches in Calabi-Yau manifolds, there was actually a different problem that was bothering people even more. And it had to do with the fact that string theory didn't seem to be one theory at all. Remember, after the first superstring revolution in 1984, people had found not one, but 5 consistent superstring theories, each living in 10 dimensions, each with supersymmetry, each free of anomalies. There was the type 1 theory, which had open strings, strings with endpoints, as well as closed strings, and it had the gauge group SO32. There was the type 2A theory and the type 2B theory, both involving only closed strings, but differing in how the left-moving and right-moving vibrations were organized. And there were the 2 heterotic theories, the SO32 heterotic string and the E 8 times E8 heterotic string that we talked about earlier. 5 theories, all mathematically consistent, all claiming to be fundamental theories of quantum gravity. And they looked genuinely different from each other. Different gauge groups, different types of strings, different spectra of particles. If string theory was supposed to be the unique theory of everything, having 5 versions of it was, to put it mildly, awkward. It's like searching for the one true blueprint of the universe and finding 5 blueprints in the drawer, each internally consistent but apparently contradictory. Some people saw this as a fatal flaw. Others, and John Schwartz was one of them, had a hunch that the 5 theories were somehow connected, that they were different faces of a single deeper structure. But in the late 1980s, nobody could prove it. The tools weren't there yet. String theory, as powerful as it was still understood mostly through perturbation theory. You could calculate what happens when strings interact weakly, when the coupling constant is small, but you couldn't say much about what happens when the coupling is strong. And the relationships between the 5 theories, if they existed, seemed to live precisely in that strong coupling regime where the math got intractable. So the field entered a second period of slow progress. Not a wilderness exactly. People were doing important technical work, exploring Calabi-Yau geometry, developing conformal field theory, discovering beautiful mathematical structures like mirror symmetry, where 2 completely different Calabi-Yau manifolds turn out to give the same physics. That discovery, in 1991, was stunning to mathematicians because it revealed deep connections between geometric spaces that nobody had suspected. Physicists were essentially handing mathematicians new theorems, derived not from rigorous proof, but from the internal logic of string theory. It was an extraordinary reversal, physics leading mathematics rather than the other way around. But the big conceptual questions, why 5 theories? What happens at strong coupling? How do you actually connect any of this to experiment? Those remained stubbornly open. And then, in March of 1995, a physicist named Edward Witten walked to the podium at a conference at the University of Southern California, and in the space of about an hour, he changed everything. What he proposed that day was so unexpected, so sweeping in its implications, that it launched what people immediately started calling the second superstring revolution. And to understand what Witten said, we need to talk about something called duality. The idea that 2 theories that look completely different on the surface can actually be the same theory in disguise. And this idea, duality, is one of the most beautiful concepts in all of theoretical physics. So let's sit with it for a moment, because once you really get it, everything that follows, M-theory, branes, the holographic principle, all of it clicks into place. The simplest version of duality to understand is something called T-duality, and it shows up when you have a string moving in a space where one of the dimensions is curled up into a circle. Remember how we talked about Kaluza and Klein, how you can take an extra dimension and roll it up so small that nobody notices it's there? Well, when a string lives in a space like that, it can do 2 things that a point particle can't. First, it can move around the circle, just like a particle would. It has momentum in that direction, and because the dimension is compact, that momentum comes in discrete chunks. The smaller the circle, the more energy each chunk of momentum costs, because you're squeezing the wavelength into a tinier space. But here's what's special about strings. A string can also wind around the circle. It can wrap itself around that compact dimension, like a rubber band around a pencil, and the energy cost of winding is the opposite of the momentum cost. The bigger the circle, the more it costs to stretch the string all the way around it. The smaller the circle, the cheaper it is to wind. So think about what happens as you shrink the circle. Momentum modes get heavier and heavier, harder and harder to excite. But winding modes get lighter and lighter, easier and easier to excite. And here's the kicker. If you shrink the circle all the way down to some critical size, and then keep going, making it even smaller, the physics you see is identical to what you'd get if you'd made the circle bigger instead. The winding modes of the tiny circle look exactly like the momentum modes of a big circle, and vice versa. There's a symmetry, a duality. A circle of radius r gives you the same physics as a circle of radius 1 over r, in appropriate units. The string literally cannot tell the difference between a very small dimension and a very large one. That's T-duality. Now, just pause and appreciate how strange that is. In ordinary physics, small is small and big is big. If you're in a room, you can tell whether it's a closet or a cathedral. But strings can't. Below a certain scale, roughly the Planck length, the very concept of smaller loses meaning, because making something smaller is physically indistinguishable from making something else bigger. It's as if space itself has a minimum meaningful size, not because there's a wall or a boundary, but because the physics wraps around and starts looking like large-distance physics again. T-duality was understood reasonably well by the late 1980s, and one of its most important consequences was that it connected pairs of the 5 superstring theories to each other. Type 2a and type 2b, for instance, are T-dual. If you compactify type 2a on a circle and shrink it, you get type 2b on a big circle. Similarly, the two heterotic theories, SO32 and E8 times E8, are T-dual to each other. So already, the five theories were starting to look less independent. T-duality was a clue, a hint that these weren't really separate theories, but different corners of something larger. But T-duality is a weak coupling duality. It works when strings interact gently, when the coupling constant is small, and perturbation theory is reliable. The deeper, harder, more exciting question was about strong coupling. What happens when you crank up the coupling constant, when strings interact violently and frequently, when the perturbative expansion breaks down? That's where S-duality comes in, and S-duality is wilder. S-duality says that a string theory at strong coupling is equivalent to a potentially different string theory at weak coupling. So the regime where one theory becomes intractable is exactly the regime where another theory becomes simple. They're the same theory, just seen from opposite ends of the coupling constant. The evidence for S-duality had been accumulating through the early 1990s. Some of it came from supersymmetry, which is incredibly constraining. If you have enough supersymmetry, certain quantities are protected, meaning they don't change as you vary the coupling. These protected quantities, called BPS states, after Bogomolny, Prasad, and Summerfield, act like landmarks. You can calculate them at weak coupling where you trust your math, and then you can ask, if S-duality is true, these same states should exist in the dual theory. And people checked, and they did. The numbers matched. The charges matched. The masses matched. It was like finding the same fingerprints at two different crime scenes, not proof beyond all doubt, but deeply suggestive. Ashoke Sen, an Indian physicist working at the Tata Institute in Mumbai, made particularly important contributions here. In 1994, he showed that certain bound states predicted by S-duality in the heterotic string actually exist, providing a concrete, non-trivial test of the conjecture. Chris Hull and Paul Townsend in Cambridge extended the duality web further, connecting string theories to 11-dimensional supergravity, a theory that had been sitting on the shelf since the early 1980s, mostly ignored by string theorists because it wasn't a string theory at all. It was a field theory, a supersymmetric extension of general relativity in 11 dimensions, and it didn't seem to have anything to do with strings. But Hull and Townsend argued that the strong coupling limit of type 2a string theory in 10 dimensions actually grows an 11th dimension. As you turn up the coupling, a new spatial dimension unfurls, and what you get is 11-dimensional supergravity. And this is exactly what Witten synthesized that day in March 1995 at USC. He took all of these threads, T-duality linking IA to IB, and the two heterotic theories, S-duality linking strong and weak coupling, the hints of 11 dimensions lurking in the strong coupling limit, and he wove them into a single picture. He proposed that all 5 superstring theories, plus 11-dimensional supergravity, are different limiting cases of a single underlying theory. He called it M theory. Nobody is entirely sure what the M stands for. Witten has been playfully evasive about it. He suggested magic, mystery, membrane, or mother, and said the M can stand for whatever you like until the theory is better understood. That ambiguity is itself a clue about the state of affairs, because here's the honest truth. M theory, as of Witten's talk and really as of today, is not a fully defined theory. Nobody has written down its fundamental equations. Nobody has a complete non-perturbative formulation. What Witten gave the community was a map showing how all the known theories fit together as different patches of a larger landscape, like different views of the same mountain from different valleys. You can see the mountain from each valley, but no one has yet climbed to the summit and surveyed the whole thing. But even as a map, it was transformative. Think about what it meant. For a decade, string theorists had been troubled by the embarrassment of having 5 consistent theories when they wanted one. Suddenly, there was one. The 5 theories weren't competitors, they were facets. And the theory they were facets of lived not in 10 dimensions, but in 11. That 11th dimension had been hiding in plain sight. When the string coupling is weak, the 11th dimension is tiny, curled up so small that it's invisible, and you see 10-dimensional string theory. When the coupling is strong, the 11th dimension opens up, and the fundamental objects are no longer one-dimensional strings, but 2-dimensional membranes, surfaces, sheets, living in 11-dimensional space-time. These membranes, or branes as people quickly started calling them, turned out to be far more important than anyone initially realized. And this is where the story takes another turn, because branes weren't entirely new. A few years before Witten's talk, a physicist named Joseph Polchinski at the University of California, Santa Barbara, had been studying objects called D-branes. The D stands for Dirichlet, after the 19th century mathematician Peter Gustav Lejeune Dirichlet, and it refers to a specific type of boundary condition. Here's the idea. When you have an open string, a string with 2 endpoints, like a tiny piece of spaghetti rather than a rubber band, those endpoints have to be somewhere. They have to satisfy boundary conditions, which are rules about how the string behaves at its edges. The traditional choice was Neumann boundary conditions, where the endpoints are free to move anywhere. But Polchinski realized that you could also impose Dirichlet boundary conditions, where the endpoints are fixed, stuck to a surface. And that surface, that object where the string endpoints are anchored, is a D-brane. Now, what's remarkable is that these D-branes aren't just mathematical conveniences. They're physical objects. They have mass. They have charge. They gravitate. They can be zero-dimensional, like a point. That's a D0 brane. They can be one-dimensional, like a line. A D1 brane, which looks a lot like a string itself. They can be 2-dimensional, like a sheet, or 3-dimensional, like a volume, and so on, all the way up to D9 branes filling all of space. And Polchinski showed, in a beautiful 1995 paper that landed just months after Witten's talk, that D-branes are precisely the objects that carry the charges predicted by S-duality. Remember those BPS states, the protected states that Sen and others had been checking? The ones that had to exist if duality was right? D-branes were those states. They were the missing puzzle pieces. So suddenly, the theory was much richer than anyone had imagined. It wasn't just strings anymore. It was strings and branes of various dimensions, all coexisting, all interacting, all part of the same framework. Open strings could end on D-branes, and the vibrations of those open strings, the ones stuck to a brane, looked, from the perspective of someone living on the brane, like particles moving in a lower dimensional world. Think about that for a second. If you had a 3-dimensional D brane, a D3 brane, floating in 10-dimensional spacetime, and you had open strings with their endpoints anchored to that brane, the physics on the brane would look like a quantum field theory in 3 spatial dimensions plus time. It would look like our world. And this wasn't just a vague analogy. The specific field theories you got on the brane were gauge theories, exactly the type of theories that describe the strong and electro-weak forces in the Standard Model. This opened up an entirely new way of thinking about why our universe looks the way it does. Maybe we live on a brane. Maybe the reason we experience 3 spatial dimensions isn't that the universe only has 3 spatial dimensions, but that we're stuck, our particles, our forces, our light, everything we interact with, are open strings whose endpoints are confined to a 3-dimensional brane embedded in a higher dimensional space. Gravity, being described by closed strings with no endpoints, wouldn't be confined. It could leak off the brane into the extra dimensions, which might even explain why gravity is so much weaker than the other forces. It's diluted by spreading into dimensions that the other forces can't access. These were wild ideas, and they were pouring out fast in the mid to late 1990s. The second superstring revolution was in full swing, and the community was electric, with a sense that fundamental questions were finally within reach. But perhaps the most stunning result of this entire period, the one that even skeptics had to sit up and take notice of, came from applying these new tools to one of the oldest and deepest puzzles in theoretical physics. It involved black holes, and it involved a question that Stephen Hawking had posed 2 decades earlier, a question that had haunted the field ever since. And that question was about entropy, about what happens to information when it falls into a black hole, and whether the universe keeps its books balanced or whether black holes are somehow above the law. The person who finally cracked part of that puzzle, using D-branes and string theory, was a young physicist named Andrew Strominger, working with Kamran Vafa at Harvard. And what they found in January of 1996 was something that had never been done before in the history of physics. They counted the microscopic states of a black hole and got exactly the right answer. Let that sink in for a moment. To understand why this was so extraordinary, you need to appreciate just how deep the puzzle was. Back in the early 1970s, Jacob Bekenstein, a graduate student working under John Wheeler at Princeton, had proposed something radical. He suggested that black holes have entropy. Now, entropy is one of those concepts that sounds abstract but is actually very concrete. It's a measure of how many different microscopic arrangements can produce the same macroscopic appearance. Think of it this way. If you have a box of gas at a certain temperature and pressure, there are an enormous number of ways the individual molecules could be bouncing around that would all give you that same temperature and pressure. The number of those arrangements, or more precisely the logarithm of that number, is the entropy. It's a count of hidden information, of all the microscopic details you can't see from the outside. Bekenstein's idea was that black holes, despite looking simple from the outside, described by just their mass, charge, and spin, must be hiding an enormous amount of internal complexity. And he proposed that the entropy of a black hole is proportional to the area of its event horizon, not the volume, which is what you might naively expect, but the area. That was already strange. Then Hawking came along and made it precise. Using quantum field theory in curved spacetime, Hawking showed in 1974 that black holes actually radiate. They emit thermal radiation, now called Hawking radiation, at a specific temperature. And once you know the temperature, thermodynamics gives you the entropy. The Bekenstein-Hawking entropy formula is beautifully simple. The entropy equals 1/4 of the event horizon area, measured in Planck units. For a typical astrophysical black hole, this is a staggeringly large number. A black hole with the mass of our Sun would have an entropy around 10 to the 77th. That's more than all the ordinary matter entropy in the observable universe. But here's the thing that bothered everyone for 20 years. In normal thermodynamics, entropy has a statistical interpretation. You can, at least in principle, go and count the microstates. You can say, here are all the different ways the molecules could be arranged. Let me count them. Take the logarithm, and I get the entropy. For a box of gas, Ludwig Boltzmann showed how to do this in the 19th century. For a black hole, nobody could do it. The Bekenstein-Hawking formula told you what the answer should be, but it was derived from the outside, from the geometry of space-time and quantum fields living on that geometry. It said nothing about what the microstates actually are. What are the microscopic degrees of freedom that a black hole is hiding behind its event horizon? General relativity couldn't answer this because general relativity is a classical theory. It describes the smooth geometry of space-time but has no concept of microscopic quantum states. And any quantum theory of gravity was supposed to provide those microstates to explain where that enormous entropy comes from. It was, in a very real sense, a litmus test. If your candidate theory of quantum gravity can't reproduce the Bekenstein-Hawking entropy by counting microstates, then your theory is probably wrong, or at least incomplete. So when Strominger and Waffe sat down to tackle this problem in late 1995, they had a very specific target to hit. They needed to identify the microscopic states, count them, and get exactly 1/4 of the horizon area. Not approximately. Exactly. And here's how they did it. They used branes. The particular black hole they studied wasn't a simple one like a Schwarzschild black hole. Those are actually the hardest to work with because they have zero charge and maximum Hawking temperature, which means they're far from the regime where you can do controlled calculations. Instead, Strominger and Waffe looked at an extremal black hole in 5 dimensions. Extremal means the black hole carries the maximum possible charge for its mass, which puts it in a very special state. It's at 0 temperature. It doesn't radiate, and supersymmetry protects many of its properties from getting scrambled by quantum corrections. This is crucial. It means you can do a calculation at weak coupling, where string theory is tractable, and trust that the answer won't change as you dial up the coupling to the point where the system actually becomes a black hole. Their setup involved wrapping branes around compact dimensions in a very specific configuration. They took a 5-dimensional compactification, so you start with 10-dimensional string theory and curl up 5 of the dimensions on a compact space. Then they considered a bound state of D1 branes and D5 branes, with some momentum flowing along the common direction. From the 5-dimensional perspective, this looks like a point-like object with mass and several types of charge. And when those charges are large enough, the gravitational back reaction of all those branes curves space-time so much that an event horizon forms. You get a black hole. Now, here's what's really clever. At weak string coupling, before gravity becomes strong enough to form a horizon, this system is just a collection of branes with open strings stretching between them. You can describe it using ordinary quantum mechanics. Well, a supersymmetric gauge theory living on the branes. But the point is, it's a system you can analyze. The open strings stretching between the D1 branes and D5 branes have various possible excitation modes, and you can count the number of quantum states at a given energy level. It's a combinatorial problem, like counting the number of ways to distribute a certain amount of energy among a collection of oscillators. And the mathematics for this had actually been worked out long ago. It involves a formula from number theory related to the partition function, refined by the specific details of the brane configuration. Strominger and Waffe did the counting. They computed the logarithm of the number of microstates, and the answer came out to exactly 1/4 of the horizon area. Exactly. Not approximately, not to leading order with some fudge factors. Exactly, including the numerical coefficient. The Bekenstein-Hawking formula, which had been derived from completely different physics, semi-classical gravity, Hawking radiation, thermodynamic arguments, was now reproduced from a microscopic counting of quantum states in string theory. Think about what that means. Two utterly different calculations, starting from completely different assumptions and using completely different mathematical machinery, arriving at precisely the same number. One calculation knows about event horizons and curved spacetime, but nothing about microstates. The other knows about microstates, branes and open strings, but was done in a regime where there's no event horizon at all. And they agree. That's the kind of thing that makes physicists believe they're on the right track. It's like finding the same treasure by following two completely different maps. The result electrified the field. Even people who had been skeptical of string theory acknowledged that this was a genuinely impressive achievement. You finally had a microscopic explanation for black hole entropy. The hidden degrees of freedom were the quantum states of open strings living on branes. And the area law, that strange fact that entropy scales with area rather than volume, emerged naturally from the brane construction. It wasn't put in by hand, it just fell out of the counting. And this was just the beginning. Over the following months and years, the result was extended. Juan Maldacena, who was a young postdoc at the time, along with Strominger and others, generalized the entropy counting to near-extremal black holes, ones that are slightly away from the extremal limit, that do have a non-zero temperature and do radiate. They computed the Hawking radiation rate from the D-brane picture and found it matched the semi-classical prediction. Not just the total rate, but the spectrum, the distribution of emitted particles across different energies and species. The D-brane model was reproducing the detailed thermodynamics of black holes, not just the entropy. This success with black holes fed directly into what many people consider the single most important theoretical development to come out of string theory. And it came from Maldacena in a paper he published in late 1997, a paper that has since become the most cited paper in the history of high-energy physics. What Maldacena proposed was a precise mathematical equivalence, a duality, between a string theory living in a particular curved spacetime and a quantum field theory living on the boundary of that spacetime. This is the ADS/CFT correspondence, and it's one of those ideas that sounds so strange when you first hear it that you almost can't believe anyone took it seriously. But they did, and it changed everything. Let me set this up carefully because it's worth understanding. A DS stands for anti-de Sitter space, which is a specific solution to Einstein's equations with a negative cosmological constant. Imagine a space-time that is curved in such a way that it acts like a box. Things naturally want to fall back toward the center. It has a boundary, and that boundary is one dimension lower than the bulk space. CFT stands for conformal field theory, which is a special type of quantum field theory that looks the same at every scale. It has no preferred length. What Maldacena conjectured was that type 2 B string theory, living in a 5-dimensional anti-de Sitter space, times a 5-dimensional sphere, is completely equivalent to a specific 4-dimensional conformal field theory, namely N equals 4 super Yang-Mills theory, living on the 4-dimensional boundary. Completely equivalent. Not approximately equivalent. Not analogous to. Not inspired by. Equivalent. Every physical question you can ask about the gravitational theory in the bulk has a precise translation into a question about the non-gravitational field theory on the boundary, and vice versa. The two descriptions contain exactly the same information, encoded in radically different ways. A black hole forming in the interior of ADS space corresponds to the boundary field theory heating up to a certain temperature. Gravitational waves propagating through the bulk correspond to disturbances in the boundary theory. The entire interior geometry, every dimension, every curve of space-time, is somehow encoded holographically in a lower dimensional theory that doesn't even contain gravity. This is why people call it the holographic principle, an idea that had been floating around since the early 1990s, proposed independently by Gerard 't Hooft and Leonard Susskind, partly inspired by the Bekenstein-Hawking entropy, scaling with area rather than volume. If the maximum entropy in a region scales with its surface area, then maybe the true degrees of freedom live on the surface, not in the volume. Maybe the three-dimensional world is, in some deep sense, a projection from a two-dimensional boundary. It sounds like science fiction, but Maldacena gave it a concrete, mathematically precise realization. And here's why this matters beyond just being a beautiful theoretical structure. The duality is a strong, weak duality. When the field theory on the boundary is strongly coupled, meaning the interactions are so intense that traditional perturbative methods fail completely, the gravitational description in the bulk becomes weakly curved and easy to work with. Classical gravity. You can just solve Einstein's equations. Conversely, when gravity in the bulk is strongly quantum mechanical and hard to analyze, the boundary field theory becomes weakly coupled and tractable. Each description is most useful precisely when the other is most difficult. It's like having a translation dictionary between two languages, where each language happens to have simple words for exactly the concepts that are complicated in the other. This turned out to be wildly useful in ways nobody initially expected, because strongly coupled quantum field theories show up everywhere in physics. In the quark-gluon plasma produced at heavy ion colliders like RHIC at Brookhaven, in condensed matter systems near quantum critical points, in the behavior of high-temperature superconductors. Suddenly, string theory had something to say about real experimental physics, not through direct predictions about strings or extra dimensions, but through this backdoor of duality. You could model a strongly coupled fluid using a black hole in anti-de Sitter space and compute its viscosity. And when people did this, they found a remarkable result. The ratio of shear viscosity to entropy density had a universal minimum value in these holographic models, and the quark-gluon plasma measured at RHIC came astonishingly close to saturating that bound. String theory, of all things, was making contact with data from a particle collider, just not in the way anyone had originally imagined. But Maldacena's conjecture also sharpened the black hole information paradox into something much more precise, and the debates that followed would consume the theoretical physics community for the next 2 decades and counting. Because if ADS/CFT is correct, then the boundary field theory is an ordinary quantum mechanical system. It's unitary. Information is conserved, full stop, which means the bulk gravitational theory must also be unitary, which means black hole evaporation must somehow preserve information, even though Hawking's original calculations seemed to show it didn't. Hawking himself eventually conceded this point in 2004, famously paying off a bet he'd made with John Preskill. But conceding that information is preserved and actually explaining how it gets out of a black hole are two very different things. And the mechanism, the precise physical process by which information encoded in stuff that fell past the event horizon eventually makes it back out in the Hawking radiation, remained deeply mysterious. It still is in many ways, though there's been remarkable progress. And some of that progress came from pushing the ideas of entanglement and quantum information theory into the heart of how we think about space-time itself, leading to suggestions that space-time might literally be woven from quantum entanglement. But that thread takes us somewhere really deep, and to appreciate it, we need to talk about a physicist named Mark van Ramsdonk and a thought experiment he proposed around 2010 that honestly might be one of the most profound ideas to come out of theoretical physics in the 21st century so far. Here's the setup. Imagine you have a conformal field theory living on the boundary of anti-de Sitter space, the kind of system Maldaceno's duality describes. Now imagine the quantum state of that boundary theory is entangled in the usual way. Different regions of the boundary share quantum correlations with each other. The fields over here are entangled with the fields over there. And according to ADS/CFT, this boundary state has a dual description. It corresponds to some particular geometry in the bulk, some particular shape of space-time in the interior. Van Ramsdonk asked a beautifully simple question. What happens to the bulk space-time if you gradually reduce the entanglement between two halves of the boundary? What if you slowly disentangle the left side from the right side? And the answer, at least within the framework of the duality, was striking. As you reduce the entanglement, the bulk space-time starts to pinch off. The geometric connection between the two sides gets thinner and thinner, like a bridge narrowing, until finally, when the entanglement reaches zero, the space-time splits into two completely disconnected pieces. No bridge, no tunnel, no geometric link at all. Two separate universes, if you like. Think about what that means for a second. It's saying that the thing holding space-time together, the thing that makes one region of space geometrically connected to another region of space, is quantum entanglement. Not matter, not energy, not some classical glue. Entanglement. The spooky correlations that Einstein himself was so uncomfortable with turn out to be, if this picture is right, the very fabric of the spatial geometry he spent a decade constructing. This connects to an older idea, actually. Back in 1935, Einstein and Rosen wrote a paper about what we now call Einstein-Rosen bridges, wormholes basically, geometric tunnels connecting two black holes, and in 2013, Juan Maldacena and Leonard Susskind proposed a conjecture they called ER equals EPR. ER for Einstein-Rosen bridges. EPR for Einstein-Podolsky-Rosen, the famous 1935 paper on quantum entanglement. The conjecture says these are the same thing. Every pair of entangled particles is connected by a tiny, non-traversable wormhole. Every wormhole is a manifestation of entanglement. Geometry is entanglement. Entanglement is geometry. Now, this is a conjecture. It hasn't been proven in any rigorous sense, but it's one of those ideas that keeps showing up in different calculations, keeps being consistent with everything people check, and has this quality of feeling deeply right to a lot of the people working on it. And it reshaped how people think about the black hole information problem. Because here's the thing. If space-time geometry is built from entanglement, then the process of black hole evaporation, where Hawking radiation slowly carries energy away from a black hole, is also a process of rearranging entanglement. And tracking that entanglement carefully turns out to be the key to understanding how information gets out. This brings us to something called the Page curve, named after Don Page, who proposed it back in 1993. Page asked a simple question about a black hole that forms and then slowly evaporates away by emitting Hawking radiation. At first, the radiation that comes out is entangled with the black hole's interior. So the entanglement entropy of the radiation, a measure of how much it's correlated with the remaining black hole, goes up. more radiation comes out, more entanglement. But here's the thing. If the process is truly unitary, if information really is preserved, then at some point, that entanglement entropy has to start coming back down. Because by the time the black hole has completely evaporated, all the information must be in the radiation, and the radiation must be in a pure quantum state, which means its entanglement entropy with anything else must be zero. So the curve goes up, reaches a maximum at roughly the halfway point of evaporation, what's called the page time, and then comes back down. That's the page curve. And reproducing it from a gravitational calculation became the holy grail of the information paradox, because Hawking's original calculation, which treated the radiation as thermal, predicted the entropy would just go up and never come back down. That was the whole problem. The curve just kept rising, implying information was being destroyed. For decades, nobody could reproduce the page curve from the gravitational side. It was this benchmark that any complete theory of quantum gravity should be able to hit, and nothing could hit it. Until 2019, when two groups, one led by Jeff Pennington and another by Ahmed Almhiri, Netta Engelhardt, Donald Marolf, and Henry Maxfield, independently showed how to do it. And the way they did it was remarkable. They used a formula for entanglement entropy that had been developed a few years earlier, called the quantum extremal surface formula, which itself was a refinement of an older idea by Ryu and Takayanagi from 2006. Let me back up and talk about Ryu Takayanagi for a moment, because it's beautiful and it ties everything together. Shinsei Ryu and Tadashi Takayanagi, working in 2006, proposed a stunningly simple formula within ADS/CFT. They said, if you want to compute the entanglement entropy of some region in the boundary field theory, you find the minimal area surface in the bulk that's anchored to the boundary of that region. And the entanglement entropy is just the area of that surface divided by 4 times Newton's constant. Does that formula remind you of anything? It should. It's the Bekenstein-Hawking formula again. Area divided by 4g. The same formula that gives you black hole entropy. And that's not a coincidence. It's telling you something deep. The Bekenstein-Hawking entropy of a black hole is entanglement entropy. The area of the horizon is measuring quantum correlations between the inside and the outside. This is one of those moments where everything starts clicking together. The black hole thermodynamics that Bekenstein intuited in the 1970s, the Hawking radiation, the holographic principle, Maldaceno's duality, and now this geometric formula for entanglement. They're all facets of the same underlying structure. So the quantum extremal surface prescription generalized Ryu Takayanagi by including quantum corrections, not just the area term, but also the entanglement of quantum fields across the surface. And when Pennington and the Almhiri group applied this prescription to an evaporating black hole, something magical happened. At early times, the minimal quantum extremal surface was trivial. It gave you the Hawking answer, entropy going up. But at the page time, a new quantum extremal surface appeared, one that sat just inside the black hole horizon. And this new surface gave a smaller entropy. The prescription says you pick the surface that gives the minimum. So at the page time, you switch to the new surface, and the entropy starts going down. The page curve, reproduced from gravity. The physics community was, I think it's fair to say, electrified. This was the first time anyone had derived the page curve from the gravitational side of the duality, and it came with a startling implication. After the page time, the interior of the black hole, or at least a portion of it, is encoded in the radiation that's already come out. the entanglement structure has shifted so that the black hole interior is no longer independent of the exterior radiation. They're the same degrees of freedom, seen from different perspectives. This led to the concept of entanglement islands, regions of space-time inside the black hole that are, in terms of quantum information, actually part of the radiation's entanglement wedge. The island formula, as it came to be called, says that the entropy of the radiation equals the generalized entropy of the radiation's region plus any islands, and the island is what makes the entropy go down. It's the black hole interior being gradually transferred, quantum informationally speaking, to the outside. Now, you might be lying there thinking, this is all very abstract. Entanglement islands, quantum extremal surfaces. What does any of this have to do with the real world? And that's a fair question. But here's why it matters. This is our best window into understanding what space-time actually is at the deepest level. We've been treating space-time as a stage, a fixed background where physics happens. But everything we're learning from string theory and its offshoots is telling us that space-time is emergent. It's not fundamental. It's built from something deeper, something quantum informational. The geometry of space, the causal structure that says this event can influence that event, the very notion of here versus there, all of it might be a macroscopic consequence of patterns of entanglement in some underlying quantum system. And if that's true, then the distinction between inside the black hole and outside the black hole isn't as sharp as we thought. The information isn't stuck behind the horizon in some absolute sense. The horizon itself is an emergent concept, and when the entanglement structure changes enough, when enough Hawking radiation has come out, the notion of inside gets reshuffled. This connects to another dramatic episode in the information paradox saga that we should talk about, because it caused a genuine crisis. In 2012, Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully, a group that became known by their initials AMPS, published a paper arguing that the standard picture of black hole evaporation contained a fundamental contradiction. Their argument was sharp and unsettling. They showed that three things most physicists believed about black holes couldn't all be true simultaneously. That information is preserved, that the horizon is a smooth, uneventful place for an infalling observer, and that physics outside the horizon is described by standard quantum field theory. You could have any two, but not all three. If you gave up the smooth horizon, then an observer falling into the black hole would hit a wall of high-energy radiation at the horizon, what AMPS called a firewall. Not the gentle passage through nothingness that general relativity predicts, but a violent, destructive barrier. This was shocking, because it seemed to violate the equivalence principle, Einstein's foundational insight that gravity and acceleration are locally indistinguishable. An observer in free fall shouldn't notice anything special at the horizon. That was supposed to be one of the most reliable predictions of general relativity. The firewall paradox consumed the community for years. Workshops were held, tempers occasionally flared. Susskind worked on it. Maldacena worked on it. 't Hooft worked on it. Hawking proposed new ideas about it, and while no single resolution has been universally accepted, the island formula and the page curve calculations from 2019 have shifted the landscape considerably. Many researchers now believe that the resolution involves a more subtle understanding of the black hole interior, that the interior geometry is not independent of the exterior, that it's reconstructed from the radiation in a state-dependent way, and that the apparent contradiction in the AMPS argument dissolves when you properly account for the quantum gravitational nature of spacetime. But notice what's happened here. We started with string theory as a theory of tiny vibrating strings, a candidate for quantum gravity. And through a chain of discoveries, branes, black hole entropy counting, ADS/CFT, holography, entanglement entropy, islands, it's evolved into something much broader. It's become a laboratory for understanding the quantum nature of spacetime itself. Even people who are skeptical about whether string theory describes our particular universe often use the tools and frameworks that string theory has generated. A DS/CFT is used by condensed matter physicists. Entanglement entropy calculations are used by quantum information theorists. The Page curve is discussed by people who would never call themselves string theorists. And this brings up a question that's been simmering in the background of everything we've discussed, one that's become increasingly urgent as the decades have passed. Does string theory actually describe nature? Can it make predictions that we can test? Or is it, as some critics have charged, not even wrong? Not even a scientific theory in the traditional sense, but something else. A mathematical framework, a set of tools, a philosophy of physics dressed up in equations. Let's sit with that question for a while, because it's genuinely important, and it's more nuanced than either side sometimes makes it sound. The traditional picture of how science works goes something like this. You observe something puzzling about nature. You propose a theory to explain it. That theory makes predictions, specific, quantitative predictions about things you haven't yet measured. You go out and measure them. If the predictions match, the theory gains credibility. If they don't, you revise or discard the theory. This is the basic Popperian framework, named after the philosopher Karl Popper, and it served physics extraordinarily well for centuries. Newton's gravity predicted the motions of planets. Maxwell's electromagnetism predicted radio waves before anyone had detected them. Einstein's general relativity predicted the bending of starlight, confirmed during the 1919 solar eclipse. The Standard Model predicted the existence of the Higgs boson decades before it was found at the Large Hadron Collider in 2012. Each of these theories stuck its neck out. Each said, "If I'm right, you should see this." And each time, nature said yes. So where does string theory stand in this picture? And here's where you have to be honest. The answer is uncomfortable. As of right now, string theory has not made a single confirmed, unique prediction about an experiment we can perform. Not one. That's not a minor quibble. For a framework that's been under development since the late 1960s, more than 50 years, that's a striking fact. And it's the core of the criticism that people like Lee Smolin and Peter Woit have raised in books and articles over the years. Smolin's 2006 book, The Trouble with Physics, and Woit's Not Even Wrong, from the same year, both argued, in different ways, that string theory had become a kind of self-sustaining intellectual ecosystem that was absorbing enormous talent and resources without delivering on its fundamental promise of describing nature. And they had a point. You can't just dismiss that criticism. But here's the thing. The situation is more complicated than string theory makes no predictions, therefore it's not science. Let me explain why. First, there's a practical issue. String theory is fundamentally a theory of quantum gravity, and quantum gravitational effects become important at the Planck scale. Distances of about 10 to the minus 33 centimeters, energies of about 10 to the 19 gigaelectron volts. For comparison, the Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 to the 4 gigaelectron volts. That's 15 orders of magnitude short. 15. That's like trying to study individual atoms using a magnifying glass designed for reading newspapers, except the gap is vastly larger than that analogy suggests. So the most natural predictions of string theory, the ones about the fundamental structure of space-time, the behavior of gravity at quantum scales, the nature of the Big Bang singularity, are simply beyond our current experimental reach. And that's not string theory's fault, exactly. It's a consequence of the energy scales involved. Any theory of quantum gravity would face the same problem. Loop quantum gravity faces it. Causal set theory faces it. It's the nature of the beast. But that explanation only goes so far. Because physicists have always been creative about finding indirect tests, unexpected observational windows, clever ways to probe regimes that seem inaccessible. And string theorists have tried. They really have. Let me walk you through some of the attempts. One of the earliest hopes was that string theory would predict the specific properties of the particles we observe. The masses of quarks and leptons, the strengths of the fundamental forces, the number of generations of matter. If you could find the right Calabi-Yau manifold, the right compactification, the right way of curling up those extra dimensions, you'd get a four-dimensional universe that looks exactly like ours, with exactly the right particle content and exactly the right coupling constants. That was the dream of the late 1980s, and for a while, it seemed tantalizingly close. People found Calabi-Yau manifolds that gave 3 generations of particles, which matched observation. They found models with gauge groups that could contain the standard model. But they never found the one. They never found a unique compactification that said, "This is our universe, and here are the precise values of all the constants." Instead, they found the landscape, that vast space of maybe 10 to the 500 possible solutions that we talked about earlier, and the landscape didn't narrow things down. It blew them wide open. Now, some physicists have tried to turn the landscape into a virtue rather than a problem. This is where the anthropic principle enters the story, and it's controversial enough that it's worth explaining carefully. The idea goes like this. If there really are 10 to the 500 possible vacuum states, and if some mechanism, perhaps eternal inflation, actually realizes all of them in different regions of a vast multiverse, then we shouldn't be surprised that we find ourselves in a region where the constants of nature are compatible with our existence. We can't live in a universe where the cosmological constant is so large that space rips apart before galaxies form. We can't live in a universe where the strong force is too weak for nuclei to hold together. So the fact that we observe life-friendly constants isn't a prediction that needs explaining by a unique theory. It's a selection effect. We're here because we can be here. This reasoning was used most prominently in connection with the cosmological constant, the energy density of empty space, which drives the accelerating expansion of the universe. When astronomers discovered this acceleration in 1998, the measured value of the cosmological constant turned out to be absurdly small by particle physics standards, roughly 10 to the minus 120 in natural units. That's a number so small, it's almost zero, but not quite. And here's what's eerie. In 2000, Raphael Busso and Joe Polchinski argued that the string landscape, with its enormous number of vacua, could naturally produce a distribution of cosmological constant values, and that anthropic selection would pick out values in roughly the range we observe. Steven Weinberg had actually made a similar anthropic prediction for the cosmological constant back in 1987, before the landscape was even known, and the observed value fell within his predicted range. So, in a loose sense, the anthropic landscape picture was consistent with observation. But And this is a big but. Most physicists find this deeply unsatisfying. It feels like giving up. It feels like saying, we can't predict the constants of nature, but that's okay, because there's a multiverse and we just happen to be in this corner of it. It's not wrong, necessarily. It might even be true, but it's not the kind of sharp, falsifiable prediction that makes physics feel like physics. It's more like an explanation after the fact, and you can construct similar explanations for almost anything. That's the worry. If your theory can accommodate essentially any observation, does it really explain anything? And this is where the debate gets genuinely philosophical, in ways that physicists aren't always comfortable with. What counts as a prediction? What counts as evidence? Does a theory need to be falsifiable in the strict Popperian sense to be scientific? Or is that criterion too narrow for the kinds of questions we're now asking about fundamental physics? Some philosophers of science, like Richard Dawood, have argued for what he calls non-empirical theory assessment. The idea that when direct experimental tests are impossible, you can still gain confidence in a theory through other means. Things like the absence of plausible alternatives, the unexpected mathematical fertility of the framework, the way it keeps solving problems it wasn't designed to solve. String theory scores well on all of these, Dawood argues. It's the only known framework that consistently unifies gravity with quantum mechanics. Its mathematical structures keep showing up in unexpected places. The tools it's generated, ADS/CFT, entanglement entropy, topological field theory, have been productive far beyond their original context. Others push back hard. Sabine Hossenfelder, a theoretical physicist who's been one of the more vocal critics, has argued that the physics community has been led astray by mathematical beauty, that the preference for elegant, symmetric theories has become an aesthetic bias rather than a reliable guide to truth. She points out that nature is under no obligation to be mathematically beautiful by human standards, and that the history of physics includes plenty of cases where the ugly theory turned out to be right. So, where does this leave us? Honestly, in a fascinating and somewhat unprecedented situation. String theory is not confirmed. It's not refuted. It occupies this strange middle ground where it's clearly the most mathematically rich and structurally coherent approach to quantum gravity we have. And yet it hasn't made contact with experiment in the way that the great theories of the 20th century did. And the question of whether it ever will is genuinely open. But here's something that I think gets lost in the loudest versions of this debate. There are potential observational windows. They're speculative, and none of them have panned out yet, but they exist, and people are actively looking. One involves cosmic strings, not the fundamental strings of string theory, but macroscopic defects in space-time that some string models predict could have formed in the early universe and stretched to astronomical scales during inflation. If cosmic strings exist, they'd leave distinctive signatures in the cosmic microwave background and in gravitational wave signals. Searches have been conducted. So far, no detection, but the sensitivity of gravitational wave observatories like LIGO and the future LISA mission keeps improving. Another window involves the detailed statistics of the cosmic microwave background itself. Inflation, the rapid expansion of the very early universe, is sensitive to the physics of very high energy scales, and different string-theoretic models of inflation make subtly different predictions for things like the spectrum of primordial gravitational waves, characterized by a quantity called the tensor-to-scalar ratio. Current and upcoming experiments, the Simons Observatory, CMBS-4, the Lightbird satellite, are designed to measure this quantity with unprecedented precision. If they detect primordial gravitational waves, the detailed pattern could potentially distinguish between broad classes of inflationary models, some of which are rooted in string theory and some of which aren't. There's also the Swampland program, which has generated a lot of excitement in the last decade or so. This is an effort led by Kumrun Vafa and collaborators, starting around 2005 and gaining significant momentum after 2018. The basic idea is clever. Even if you can't identify which specific vacuum in the landscape corresponds to our universe, maybe you can identify which low-energy theories are not in the landscape at all. Theories that look consistent from a low-energy perspective, but that can't actually be embedded in a consistent theory of quantum gravity. The space of such inconsistent theories is called the swampland, and the boundaries between the landscape and the swampland are defined by what Vafa calls swampland conjectures, proposed constraints that any theory compatible with quantum gravity must satisfy. Some of these conjectures have startling implications. One of them, the de Sitter conjecture, suggests that stable de Sitter space, the kind of gently accelerating universe we seem to live in, might actually be impossible in string theory. If true, that would mean the current acceleration of the universe isn't driven by a true cosmological constant, but by something dynamical, something that's slowly changing, and that is, in principle, testable. If dark energy isn't constant but evolving, future surveys like the Dark Energy Spectroscopic Instrument, or DESI, and the Euclid satellite could detect the variation. In fact, some early DESI results released in 2024 hinted, very tentatively, at possible time variation in dark energy, which sent a ripple of excitement through the community, though it's far too early to draw conclusions. So the picture isn't as bleak as the strongest critics suggest. There are threads connecting string theory to observation. They're thin, and they might not hold. But they're there. And meanwhile, the theoretical insights keep coming. The understanding of black hole information, the emergence of space-time from entanglement, the unexpected connections between gravity and quantum information. These aren't just mathematical games. They're telling us something deep about how nature works at its most fundamental level. We just don't yet know exactly what. And there's one more development that I want to tell you about, because it brings together so many of the threads we've been following, and it points toward where the field might be heading next. It involves a concept called complexity, specifically quantum computational complexity. And the reason it matters here is that it offers a new lens for understanding the interior of a black hole, the very region that has been the most mysterious, the most paradoxical, the most stubbornly resistant to description in all of theoretical physics. Let me set this up for you. We've talked about how the boundary of a black hole, the event horizon, encodes information about everything that fell in. We've talked about how entanglement between the boundary theory and the interior seems to be what stitches space-time together. We've talked about how the Ryu-Takayanagi formula connects the area of surfaces inside the bulk to the entanglement entropy of regions on the boundary. And all of that is beautiful and powerful, but there's a problem. Entanglement entropy, as a quantity, saturates. It reaches a maximum and then just stays there. For a black hole that's been sitting around for a very long time, not much is changing from the perspective of entanglement entropy. The boundary theory reaches something close to thermal equilibrium, and the entropy just plateaus. But here's the thing. The interior of the black hole doesn't stop evolving. If you could somehow peek behind the horizon, the geometry in there keeps getting more complex. The Einstein-Rosen bridge, that wormhole connecting two sides of an eternal black hole, keeps getting longer. It stretches and stretches, growing linearly in time for an almost incomprehensibly long duration. And entanglement entropy can't capture that growth because entanglement entropy has already maxed out. So there's something happening inside the black hole that the tools we had weren't tracking. Something is growing, and it isn't entropy. Leonard Susskind, who by this point in our story you've heard from several times, he's the one who proposed the holographic principle, who fought Hawking over information loss, who helped develop the complementarity idea. Susskind proposed around 2014 that the quantity tracking the growth of the black hole interior is computational complexity, not entanglement. Complexity. Now, what does complexity mean here? Think of it this way. Imagine you have a quantum system, say, a collection of qubits on the boundary. The system starts in some simple reference state, something easy to describe. Then it evolves in time according to the rules of quantum mechanics. As it evolves, the state becomes more and more complicated, not more entangled necessarily. The entanglement might have already reached its ceiling, but the state itself becomes harder and harder to prepare. If you wanted to build that state starting from the simple reference state, you'd need to apply more and more quantum gates, more and more elementary operations. The minimum number of gates you'd need, that's roughly the complexity of the state. And Susskind's conjecture, which he developed with collaborators including Adam Brown, is that this computational complexity of the boundary quantum state is dual to the volume of the Einstein-Rosen bridge in the bulk. As the wormhole grows longer, the complexity grows. As the state becomes harder to prepare, the interior becomes larger. This is sometimes called the complexity equals volume conjecture, or CV for short. There's also a refined version called complexity equals action, or CA, where instead of the volume of a spatial slice through the wormhole, you compute a certain gravitational action over a specific region of spacetime called the Wheeler-DeWitt patch. The details differ, but the core idea is the same. The growth of the black hole interior is tracking the growth of quantum complexity on the boundary. Think about what that means for a second. It's saying that the size of space inside a black hole, actual geometric volume, is a manifestation of how computationally complex a quantum state is. Geometry is complexity. The fabric of spacetime, at least in this context, isn't just woven from entanglement. It's woven from the difficulty of computation. That's a wild idea, and it connects fundamental physics to quantum information theory and computer science in a way that nobody anticipated even 15 years ago. Now, complexity is a notoriously slippery concept. In classical computer science, we have well-defined notions of computational complexity, how many steps an algorithm takes, how problems scale with input size, the famous P versus NP question. But quantum complexity, the complexity of quantum states and quantum circuits, is still being developed as a rigorous mathematical framework. And applying it to continuous quantum field theories, which is what lives on the boundary in ADS/CFT, is even harder. There's been a huge amount of work trying to make these conjectures precise. People like Michael Nielsen, who did pioneering work on quantum complexity geometry, and more recently, researchers like Shira Chapman, Hugo Marocchio, and Robert Myers have been pushing the technical machinery forward. It's an active, evolving field, but the intuition is compelling, and it resolves a real puzzle. Before complexity entered the picture, people had no good boundary quantity that could track the long-time growth of the black hole interior. Entanglement wasn't enough. Complexity fills that gap, and it does so in a way that connects to deep questions in computer science, questions about how hard it is to reverse a computation, how long it takes for a quantum system to explore all of its possible states, how chaos and scrambling in quantum systems relate to the fundamental limits of computation. Susskind, in fact, has speculated that there might be a deep connection between the second law of thermodynamics, the tendency of entropy to increase, and what he calls the second law of complexity, the tendency of complexity to increase. Entropy increases until it reaches its maximum, which happens relatively quickly for most systems, but complexity keeps increasing long after entropy has plateaued, growing linearly for a time that's exponential in the number of degrees of freedom. For a black hole, that's an unimaginably long time. Eventually, even complexity would plateau. There are only so many distinct quantum states the system can explore, but the timescale for that is so vast it dwarfs the current age of the universe by factors that are themselves hard to comprehend. So here's the picture that's emerging, and I want you to just let it wash over you, because it's really something. Space-time, the arena we live in, the stage on which everything happens, might not be fundamental. It might emerge from quantum information. The connectivity of space, the fact that nearby points are near each other, might come from entanglement. The volume of space, especially in the extreme environment inside a black hole, might come from computational complexity. And the dynamics of space-time, the way geometry evolves and ripples and curves in response to matter and energy, might be a reflection of how quantum information is processed, scrambled, and transformed on some fundamental boundary-like structure that doesn't itself live in space-time at all. This is sometimes called "it from qubit," a phrase that riffs on John Wheeler's old slogan, "it from bit," the idea that physical reality at its deepest level is informational. The modern version, championed by people like Susskind, Maldacena, Patrick Hayden, John Preskill, and many others, takes this further. It from qubit. The fundamental stuff isn't particles or fields or even strings. It's quantum information. And space-time, matter, gravity, all of it, emerges from the patterns and processing of that information. Now, I want to be honest with you, because that's what we've been doing throughout this whole conversation. This picture is beautiful. It's mathematically rich. It's led to genuine insights, real theorems, actual calculations that check out. But it's also incomplete. We don't have a full theory of quantum gravity. We don't have a background-independent formulation of string theory that works in our actual universe, a universe with a positive cosmological constant, a universe that's expanding and accelerating, a universe that is decidedly not anti-de Sitter space. A DS/CFT is our best understood example of holography, but our universe isn't ADS. It's closer to de Sitter, and building a version of holography that works in de Sitter space has been one of the great open challenges. People like Andrew Strominger, Eva Silverstein, Shidong, and others have made progress, but a fully satisfactory DS/CFT, a holographic dictionary for universes like ours, remains elusive, and string theory itself, as a unified framework, still hasn't told us why the universe has the particular properties it does. Why 3 large spatial dimensions? Why these particular particles with these particular masses? Why this amount of dark energy? The landscape of solutions is vast, and we don't have a selection principle. We don't know if the anthropic approach is the right answer, or a cop-out, or something in between. These are real, hard, unsolved problems, and anybody who tells you otherwise isn't being straight with you. But here's what I keep coming back to. Think about where we started. We started with a simple, almost naive question. What happens if the fundamental objects in physics aren't point particles but tiny vibrating strings? That one idea, born out of Veneziano's formula for the strong force in 1968, a formula that was originally wrong about what it described, that one idea led to the discovery of extra dimensions, supersymmetry, the holographic principle, the emergence of space-time from entanglement, the connection between gravity and quantum information, new mathematics, new insights into black holes, unexpected tools for studying nuclear physics and condensed matter, and a complete reconceptualization of what space-time might actually be. Not bad for a wrong formula. And think about the people. Veneziano, scribbling in his office, recognizing Euler's beta function in scattering data. Nambu, Nielsen, and Susskind, independently realizing that the formula described strings. Schwartz, stubbornly working on string theory for a decade when almost nobody cared. Green and Schwartz, finding anomaly cancellation in 1984 and igniting a revolution overnight. Witten, seeing the 5 string theories as facets of one deeper thing. Polchinski, discovering that the theory had been hiding branes in plain sight. Strominger and Vafa, counting black hole microstates and getting Bekenstein and Hawking's answer exactly. Maldacena, proposing a duality so powerful that it redefined what it means to study gravity. Van Ramsdonk, showing that without entanglement, space-time falls apart. And Vafa, trying to map the boundaries of what quantum gravity allows and what it forbids. These are real people who spent real years, decades in many cases, wrestling with problems that might not have answers in their lifetimes. Some of them faced professional risk. Some of them were told they were wasting their careers. Some of them followed hunches that turned out to be spectacularly right. And some followed hunches that led nowhere, and often the same person experienced both. That's what the pursuit of fundamental physics looks like. It's not clean. It's not linear. It doesn't always produce testable predictions on a convenient schedule. But it's genuine. It's humans trying to understand the deepest structure of reality with the best tools they have: mathematics, physical intuition, and a willingness to be wrong. So as you're lying there, maybe drifting in and out, maybe you caught every detail and maybe you caught a quarter of them. Either way is fine. Here's what I'd want you to take with you into sleep. The universe is stranger than it looks. The space around you, the time flowing past you, the matter you're made of. None of it may be what it appears to be at the deepest level. There might be extra dimensions curled up too small to see. The particles in your body might be the vibrations of objects so small that no microscope could ever resolve them. The space-time you're resting in might be woven from quantum entanglement, stitched together by information, shaped by complexity. And the whole thing, all of it, might be a holographic projection from a boundary you could never reach or touch. We don't know yet. We might not know for a long time. But people are working on it. Right now, tonight. In offices and on chalkboards, and in the quiet of their own minds, turning these ideas over, checking the math, following the threads wherever they lead. And the story isn't finished. It's still being written. You just heard a piece of it. One long, winding, incomplete, beautiful piece of a story that started with a guess about strings and led to questions about the nature of reality itself. And wherever it goes next, whatever the answer turns out to be, it will have been worth the asking. So let that settle. Let it go soft and quiet, and sleep well.